Hey, Alan. Okay. Anyway, does any of these that just pop out at you? So, like I said, when I was your age, I really, I loved the movies that had radiation because I thought that would happen. Then I found out later it was sad. It was sad. Not really, but it was a little bit sad. That didn't happen. It didn't happen like they said. But okay. All right, we're going to start, and I think I gave everybody 2 handout sheets. Now, here they are. So if you have these out, this is going to be our book for part 1. Part 1 of nuclear is not in your book. It came from another book. And I made the choice to start with this one because I think you'll understand radiation better and nuclear chemistry a little bit better. And then we get to your book in part 2. Then we actually get into some of the mathematical stuff, and they actually do. I haven't used natural logarithms for, I don't know, 50 years. And some of you will use that because you're, haven't you guys done that in calculus? You guys use natural log?
Yes.
I haven't for a long, long time. And so I'll even show you a way of not using natural log. And you said, oh, I like that better. But anyway, we'll do that in part 2. All right, so here we go. Real quickly, the drawing, the photograph itself, you actually can have a cooling tower and not have a nuclear power plant, okay? So if you burn coal and you have to cool the water, Duke Power probably has a cooling tower somewhere, but they also have a nuclear reactor. Do you know that? Duke Power does produce some of its electricity with nuclear. And you could actually look on a map and find lots of nuclear power plants across the United States. If you go to France, you'll see even more. They have a lot of them. Some countries they bought into it. They said, I'm not burning that fossil fuel. I'm not doing that. And they might save 60% of their energy might come from nuclear. Yes. Yeah, go ahead. I just made that number up.
I read that France gets 70% of its energy from nuclear energy.
Oh, I just made that up. Okay, 70. Okay, now I'll use a new number.
Switzerland gets 40%.
Who?
Switzerland.
What's us? Less than 10?
I don't know, not a whole
10?
bunch. It kind of got smeared in the 70s, and so there's been no new research into it.
One thing is, for a while, we were building new plants, okay? And then there was a big, to-do about radiation and accidents, and I agree, sabotage, and I agree. The problem is, if you have a nuclear power plant and something goes wrong, how long do you have to wait to fix that mistake? 50,000 years? Some people said, I don't think that's worth it. I'm not sure I'm sold on it all. I'm not sure I'm sold on nuclear. Not fission. Fission, I'm not sure I'm sold on because a mistake is going to be there for a long, long time.
There's that big fusion reactor they're making in France.
And what now?
There's a big, it's not part of the European Union, but there's a big fusion reaction fusion reactor that they're making in France. It's America, France, Belgium, Switzerland. They're all combining and working on it.
Why would we want to build that? We don't get any of that.
Because, well, no, we do get some of it.
Oh, we do? How?
I think America's fault, but I mean it's.
How are you going to get electricity come from there?
Pay us a lot.
Okay. But you know what? You've done more reading than I have.
Well, this is part of my thesis last year.
Oh. Wow. I'm not calling you several things. Well, let me tell you about, I do like fusion. And we haven't talked about either. I do like fusion. But fission is a problem for me, and I think you'll be a little scared if you look up where the nuclear power plants are in the United States. Because you're going to see a lot of them right around Lake Michigan. A lot. Why? It has a source of water. I can use the water to cool off things, right? But I don't know if you think you understand what a treasure we have. The Great Lakes are a treasure. Why? What's in there, Great Lakes, that most people don't have? Uh-oh, I lost you on this one. Fresh water. Fresh water means not salt water. You hear that? Fresh water. It's a treasure. We have this huge reservoir of fresh water. And if we need water, we can get it from there if we had to. Other countries, they don't have that. They have the ocean all around them, right? What are you going to do with the ocean water? Well, you got to spend a lot of money to take the salt out to get your water out of it. See that? Do you know Saudi Arabia even takes money to go capture icebergs and bring them in? And a lot of it melts before they get there, but a lot of it's under the water anyway. And they take that's fresh water, because when water freezes, it doesn't freeze the salt. Salt gets pushed out. And so fresh water is a treasure, but it might scare you a little bit to find the maps of where the nuclear power plants are. Lake Michigan? Ooh, 15, 20 nuclear power plants? Oh, wait a minute. One of them has a mistake. What happens to all our fresh water? Ooh, you won't be drinking that for a while. Ooh. So I'm not sold on nuclear at this point, even though I will say it's probably the most heavily regulated industry in the United States. They have more rules, safety rules, and redundancy than any other thing I've ever seen. So if humans can make something that won't break, and we can't, but if you're going to make something that won't break, that has so many rules, it probably won't break, probably. But humans have never made something that didn't break, never. So anyway, I'm not trying to scare anybody. I'm just saying that I'm not sold on this. If they could figure out a way to do fusion, which has no radioactive waste, I would go to it right away. I'd start putting lots of money into it. Right now, it costs too much. You spend $1 million and you get $100 of energy out. I don't think we're going to do that. So we need to spend, if we can spend $1 million and get $1 million worth of energy, then we'll do it. But nobody's going to put $1 million into something and get $100 worth of energy out. You're just going to be bankrupt. Okay, so let's go here, and that's enough for there. We talked about the people. Röntgen's name is always associated. So if you ever get on Jeopardy, and they talk about first person to discover X-rays, one of the units of X-rays is called a Röntgen anyway. So his name Röntgen, and then remember the Becquerel. His name was Becquerel. This is a situation where they had a rock, and the rock was, I don't know if he did, some of it did it on purpose, but what happened to the photographic film? It was in a dark room. There was no light that got to the film. But when they developed the film, it looked like somebody shined a light on the film. Where'd that energy come from? The rock. So what is this? And actually the phrase radioactivity, yeah, here it goes. So radioactivity came up, and we said it's radioactive. Then you have the Curies, and you think you remember some of that anyway. They use the word radioactivity. And the Curies actually discovered some new elements. And I think I told you this yesterday. If you look at the periodic table, everybody look up here? Okay. What I told you yesterday is that every element up here has isotopes, right? But isotope doesn't mean radioactive. This guy has 3 isotopes. 2 are kind of stable. 1 is unstable. It's radioactive, isn't it? Now, I don't memorize the rest of them. See that? I happen to know there are 2 carbon ones. Carbon 12, it's very stable. Carbon 14, radioactive. Okay, I know that one. I'd have to look up the rest of them. I don't know osmium. I don't know. I had to look it up. But I do know that once you get to 83 and beyond, every isotope of every element is radioactive. There is no such thing as non-radioactive uranium. There's no such thing. Now, another one I'll show you is another dividing line right here. Uranium is the highest atomic number. It's the highest naturally found element anywhere in the planet, meteorites. We've never seen any element bigger than uranium. Whoa, 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 whoa. What about these, huh? Well, we didn't see those naturally, but we know how to make them. They make them synthetically, right? They're synthetic elements. And so, and you might say, well, why are they doing that? You know, it costs a lot of money. Because we never know. We never know what's going to happen if we make the next element. For example, when they learn how to make this guy right here, all right, good and bad news, plutonium. It's the most poisonous material on the planet. Ooh, bad news. Good news, it makes really good bombs. Boy, that's bad news too. Okay, but anyway, so we can actually, there's an article, I may or may not have time for you to read it, and because it's about 20 years old, but it talks about how they made new elements and stuff like that. And scientists they believe that somewhere around 125, if we can go up somewhere around 125, some theoretical chemists or physicists say there could be a zone of stability. you could be making elements that actually are more stable than all the other radioactive ones. Now, I'm not a theoretical chemist, but that zone of stability, some people predict that could happen. Hey, come on in.
Did you get a bunch of shirts?
What?
Did you get shirts delivered to you?
Yes.
Oh, I guess I did.
Okay.
Oh,
Well, I'm interrupting in the middle of your class.
No, that's
We
fine.
do this at the end of class, but some of my guys, they're mixed up. We didn't.
oh, all right, you want to check those?
I'll do it. I'll do it.
Okay, okay, okay,
I'll do it. My guys are supposed to be studying for a test, and they're not.
okay. Well, thank you for doing that.
Not. Do you mind if I walk around and pass these out while you're talking?
No, I don't mind.
Okay.
Hey, I didn't even notice. You're so nice. You are so nice. You sat there with that big mountain next to you. You said,
She
"Right?"
is so nice. Not to read everyone's middle names.
Okay. I just thought, I just looked over and I said, I must be your coat or something. I didn't even think about what that was. Okay, wait, what was I saying? Oh, yeah. So there's some scientists that believe that if you can make elements that are really big, you might get something brand new, elements that are not even radioactive. And who knows what we can build with those? And again, that's theoretical, isn't it? Right now, we're at 118. Maybe they're scratching the surface on maybe one, I don't know, maybe, but yes.
Do they have, like, why, if they were stable, why wouldn't they have already been created in, like, a storm?
Oh, man. What a great question. Now, you're way beyond what I'm ready to teach today. But I was going to ask you, where do we think different elements come from? And, okay, I'm not going to do that today, but we are going to do that. But what a great question. If you think they're stable, then why wouldn't they have been created somewhere in the universe by some huge star exploding or something? I know.
You'd be able to see their signature, right?
That's a great question you had. That's even better than people think, because fusion, which is the sun, it makes new elements there, but there's a limit, and there's a limit to those elements. So you can't make some elements that way. You have to make them a different way. So, wow, you're way ahead of the game here. All right. Anyway, let me get into this real quickly. So here are some words you're going to hear, and anybody who reads about radiation, what my goal is today is so I can teach you enough about radioactivity and how to do a nuclear equation. You could pick up any book and say, I think I know what they're saying here, okay? So we're going to do some nuclear equations today. Now, they seem to be, there were three named radiation types, okay? Now, unlike blood types, guess what they did with blood types? Oh, this blood has this chemical, we don't know what it is. What do you want to call it? A. Oh, here's another one. It's different. What do you want to call it? B. What do you want to call the other one? It doesn't have A or B. All right, nothing. And so what do we have? The blood system? A, B, O. That's creative. No. So what happened with radiation? What do they call the first kind of radiation? Alpha. What they call another kind of radiation is different. Beta. And then the other one they called gamma. Okay, now we get that. Now, so what is alpha? An alpha particle, here it is right here. An alpha particle is 2 neutrons and 2 protons. Now, you're going to hear that a lot, okay? You have to remember that an alpha particle is 2 neutrons and 2 protons. Now, a nuclear chemist would say this. They might draw one of these, and they might draw something like that, and that means alpha to them. Or they might even do this. Now, this means that the mass of this particle is 4, and the number of protons in this particle are 2. So they might do that. Now, another nuclear chemist might say, wait a minute. Yeah. Now, what is that? What's that He42? What are they trying to tell me? If you're reading about nuclear chemistry, we're not talking about electrons. We're not talking about electrons and forming bonds. You get that? So what does that mean? What part of that?
The nucleus.
That's the nucleus of a helium atom. And so one of the symbols for an alpha particle would be that. And another book would do this. They're both alpha particles. You get that? Now, imagine something that's radioactive, And that means that the nucleus is not stable, and you didn't do anything. Even if you cough on it, it's not going to make it happen. It's just spontaneously, one of them will say, whoop, and it throws off an alpha particle. Matter of fact, it changes to a new element, doesn't it? It has 2 less protons, new element, and it has 4 less mass units. Got it? Now, what happens to alpha radiation? Well, it can hurt you. If you drink it, if it stays in your body all the time, it can actually destroy lots of cells, and that might cause damage, but you'd have to have a lot of in you and have to stay there for a while. As a matter of fact, it even says in the book that a piece of paper, if I had some alpha radiation here, see? Even a piece of paper would stop it. It'd hit there, and as a matter of fact, even going through the air, it would slow down and pick up electrons and become a helium atom. So alpha is a type of radiation that could hurt you if it stayed in contact a long time with you, but if it's sitting over there, probably okay. Or they wear these suits, right? I can be okay. Even clothing sometimes stops most alpha radiation. So I'm not in danger if it's over there. I would be in danger if I put it in my body. Now, what does this little picture show? Can everybody move, everybody on this page right here? The 3 kinds of radiation, if we were to pass it through an electromagnet, or any kind of magnetic field, what is this guy here? Why is he going that way? Why is he seen to be attracted to the negative pole? Because what charge does an alpha particle have? It has to be, because that's no charge. 2 protons, it's positive. So all alpha particles are positively charged. So in a magnetic field, they would be deflected this way. There's another kind of radiation called a beta particle. Now, beta particles, one way of saying beta is to make the Greek letter beta, and you would say 0 minus 1. Now that's weird. Now, what in the heck is a beta particle? I'll give you another symbol they use. Another symbol would be this. Wait a minute. What are you talking about here? You have no mass? Your particle essentially has almost no mass. And how many protons? -1. There's something wrong here. Does anybody know what a beta particle is made of? You're not going to like this. You're not going to like it. Somebody, what is it? Yes. Now, wait a minute. I'm not talking about the electrons that are in the first energy level or the second energy level. I'm not talking about the electrons that form chemical bonds. I'm talking about an electron that comes from the nucleus. What? You didn't tell me there were any electrons in the nucleus. Well, not officially. They're not. But guess what can happen? A neutron can turn into a proton and an electron. Whoa! You're making this up. No. So when I say a beta particle, it means a neutron has decayed, and guess what? The neutron has a mass of 1, and the proton has a mass of 1, and this has a mass of 0. See that? And so a neutron can decay into a proton and a beta particle. Now the beta particle is very small. It's like an electron, isn't it? And it's actually can penetrate pretty well. So it would actually go through this piece of paper. But if I had a piece of aluminum foil, I could stop it. So if I had a special suit that had a little foil on it, I could be protected from alpha and beta radiation. Yes?
So why doesn't it travel the way electricity does?
Well, even electricity for us is to get the electrons to move through a wire. Is that what you mean?
Well, yes.
We still have to push them. They have to have some kind of a voltage that wants them to go. There has to be a reason why they go from one place to another. That's called a potential difference. I don't want to get into electricity, but there has to be a reason why electrons would want to go here. So we have to set up a circuit with a battery in it. That's a good question. Could we, if something gave off a lot of beta particles, Could we somehow capture those and produce, I never heard that. Nobody's ever asked me that. That's interesting. Okay, so anyway, the beta particle, a little bit more penetrating, and we have to be a little more careful with that, okay? It can hurt me a little bit more. And in a magnetic field, what did it do? Did it go toward the negative end of the magnetic field? It went toward the positive end because it itself is negative, isn't it? All right, now, what about the third kind of radiation? Alex, you with me today? You had a big lunch, didn't you? Did you eat your lunch yet? Okay. Sometimes you get a big lunch, you know. What about the third kind of radiation? Gamma, what's that? You haven't read any of this, have you? Okay, that's all right. Gamma that'll hurt you. Gamma is not a particle. Gamma is light. Gamma is light. And the light has a wavelength that is really, really small. Do you remember in physics, and remember what we said about red light has a bigger wavelength than violet light? Remember that? Red, violet. But the bigger the wavelength, okay, the smaller the wavelength, the higher the frequency, the higher the energy. So this guy has much more energy in it than red. And so a photon of violet light would have more energy than a photon of red light. Can you imagine a photon of X-rays? Huge amount of energy. Now go lower than that. Go lower wavelength than X-rays. What do you have? Gamma. Gamma wavelengths are incredibly small, and their energy is incredibly high. So when they go through your body, they do all kinds of damage. They can go right through your body. And as they're going through there, hundreds and thousands of molecules get destroyed. And eventually, if you're exposed long enough, hundreds of thousands of cells will be destroyed. And if enough of them are destroyed, your organs will shut down, and then you will shut down. So sorry, Kyle, but if I put a piece of plutonium right there where Kyle was, and I said, we're going to stay here for 2 hours, well, Kyle would be dead first. Sorry, Kyle. And then what would happen is the ones closest to that would die next. But all of us would probably die within a few days. If we stayed here for 2 hours and exposed to plutonium for 2 hours, and you say, I don't get it. I don't, what hit me? Why am I dying? And all that gamma radiation is coming out there, as it passes through your body and destroys more and more molecules, more and more cells, you'll start feeling sicker and sicker. And then eventually you won't feel well. And then your immune system will shut down. And then you might even die from that. But you can die from being exposed to radiation too much. Yes?
So, something I've always been a little confused about is why both infrared and
Ultraviolet?
will move through objects very easily. There's
I don't know if I've read that. I wouldn't say that infrared moves to objects like X-ray. X-ray, the wavelength's so tiny. If these are two atoms, the wavelength's so small, it just goes right in between the atoms. But I don't think I've ever read that infrared can pass through items. Infrared can hit an object and excite it and make it hotter, and then that heat might be transferred through something. But if anything, ultraviolet would have a smaller wavelength. So if it's going to penetrate, ultraviolet would be better than infrared. But I think you might be talking about cameras. Like a house gives off all kinds of light, and my eye sees visible light. My eye doesn't see infrared. So I could actually, they have these cameras, and the Army uses them. They're pretty neat. We think there's some people in that building. Okay, so you put the infrared on there, right? And their body's giving off heat. Well, the infrared will make the wall warmer, which will eventually be picked up on my camera. And so I don't know if it's not like X-rays, but they're there because their heat is hitting the wall, and so if they were to move around enough, I don't know, that's a good question. How much real time do I get on infrared? But I'm not sure it penetrates. I just think it can be transferred from inside the building to the outside of the building, like that. All right, let me go to another section now. So what I'm going to do is I'm going to switch over to this packet, and I'd like to show you in the next 15 minutes here how can you understand a book. If you were to read a book about radioactivity and radioactive reactions, how do you understand it? So let's try it. First of all, not humans, but naturally, do you know that some things are radioactive naturally? Now humans, we made some things. Whoa, we made some things that are very radioactive. All right, we made that. But you know there are things that are naturally radioactive? Okay, I got that. Do you know that without you doing anything, all right, you know that uranium can turn into thorium? Now let's watch this, all right? We're going to show you how to do you know how to balance a regular equation? This is different. We're going to balance a nuclear equation. Here's how you do it. We have to balance the top row numbers and the bottom row numbers. Ready? Uranium 238, the isotope U-238, is going to turn into another element by emitting, okay, or the emission of alpha particles. So what kind of a radiator is it? It's an alpha radiator. What kind of radiation comes from uranium-238? Alpha radiation. So watch. This is going to turn into this and throw this away, isn't it? It's going to give this off, isn't it? Let's watch how do you balance a nuclear equation? Watch the top numbers. I have a total mass of 238. You have a mass, I'm going to cover this up. You have a mass of how much? 4? Then there must be underneath my finger something that has a mass of what? 234. Whatever it is has a mass of 234. Now let's do the bottom numbers. Ready? I have 92 protons. How many do you have? Then how many are left? 90? Okay, and look on the periodic table. What element's number 90? There we go. Whoa. That gets a little trickier, but that's the basic one. Yes?
So in these situations, we're just looking at one uranium molecule. What would happen if there were several? I mean, 'cause
Even though we'll tend to talk about half-life, half-life is weird because if I had 100 uranium-238s, and let's say, let's pick another one. Let's say I had a half-life of 10 seconds, okay? And I had all these radioactive things here. 10 seconds later, half of them would have decayed into another element.
so
That means there are 50 radioactive ones left and 50 of another element.
okay.
Now, I know what you're thinking. In another 10 seconds, what should happen? 50 of these, because 50 did it in the first 10 seconds, and I can't explain this exactly, but only half of that 50 will decay in the next 10 seconds. And now there's 75 that are new and 25 that are old, and in the next 10 seconds, only half of that 25. Now, and by the way, we have to be careful because you might say to yourself, when you get down to 2, I know what's going to happen. One's going to decay. You're wrong. They might both decay. You're thinking about pure mathematics, aren't you? In the real world, they might both decay, or neither one of them might decay.
So my question is more, what happens to those helium particles, or those alpha particles, if they're like bouncing around, they're going to hit those other uranium molecules. What's going to happen?
Well, this guy, he could do damage in my body, or if there's nobody around, he'll just be given off, and he'll probably slow down as he goes through the air. See, he's hitting air. He'll probably capture a couple electrons and just become a helium atom. You know what's really weird? There's almost no helium in the atmosphere, and yet I can go to the dollar store. I could buy 10 helium balloons right now. Where are you getting that helium? There's no helium in the air. There's a lot of nitrogen in the air. Give me a nitrogen balloon, I'll make that all day. Oxygen, yeah. There's almost no helium in the atmosphere. Where are we getting all this stuff? I'm going to like it. Where's it come from? Radioactive elements. See? What? I go to the dollar store and get helium for $1. And it's not like everywhere. Yes?
Does temperature have an effect on?
Okay. And even though I'm not doing half-life there, the answer is no. At this point, temperature doesn't affect it, pressure doesn't affect it. So, and we will talk about half-life, but just not today. But that's a great question. You guys have great questions. I hope you like this. All right, next one. Look at this right here. We say uranium was naturally transmuted. What's transmutation? What's that mean? Change from one element to another. You get that? All right, and changing the thorium by alpha emission. What's that mean? Okay, so we say that uranium decayed. It decayed into thorium. You get that? And so when you see a nuclear equation where this turns into something and something else, it decays. Now later, look at this one. Look at this one. Notice that I'm doing something and letting it run into something. What am I doing there? Okay, now in 1911, remember this guy named Rutherford? Remember the gold foil experiment? Rutherford? All right, he did this in 1911. He bombarded. He knew that some kind of radioactive rock, because of the Curies, he knew that it was giving off lots of alpha particles, okay? So what he did is he put it in a container with nitrogen, like from the air. And then he analyzed that air later, and he said, I didn't put any oxygen in there, but I found oxygen. And so he eventually made the conclusion that the alpha particles bombarded the nitrogen 14 and turned it into what? Let's try again. 4 plus 14 is what? 18. Oh, wait. He found out it gave off a proton. What's a proton? What's a proton? Sometimes they draw it like this. Sometimes that's the symbol for a proton. What's another symbol for a proton? Oh, I get it. An alpha particle is the same as the nucleus of a helium atom. A proton is the same as the nucleus of a what? Hydrogen. Oh, I get it now. I get that game you're playing with me. So this saying would actually transmute nitrogen into oxygen and give off a proton. Let's count them up. Ready? 18 equals 17 plus 1, right? Here's 1. This has to be 17. Let's go with the bottom numbers. 9 has to equal 1 plus what? 8. What element's number 8? Oxygen. Okay, now how do you do that in English? Ready? How do you say it in English? Nitrogen atoms were bombarded with alpha particles from radioactive material, forming, what did they form? What isotope of oxygen? Oxygen 17, and it should say a proton, but you know what the proton's going to do? It's going to capture an electron and become a hydrogen atom. See that? Okay, let's do the next one.
So, would the oxygen atoms be an ion? Or
Okay,
would they-
great question. That's a great question. And also, this, if you made another one, I don't see any reason why chemically, not nuclear, but I don't know why chemically another two of them together wouldn't make O2. And I think you would have O2. So that's a great question about, I still have electrons. There are electrons there. I guess I've never read about, I guess I've never read about, this guy had, I would assume he would have 7 electrons. And you have no electrons. So somehow I got to have 8 electrons with oxygen here. I have 8, so I had to pick one up from somewhere. That's a great question. I don't know the answer. I'd look at it. Okay, let's do the next one. Solar particles can naturally cause transmutation in the atmosphere. And here's another player. Okay, here's another player in the game. And what is he called? What's N10? What would you call that? So there are things that can be given off, like neutrons can be given off too. So let's see what happens. What would happen if you bombarded nitrogen 14 with a neutron? Let's see, 14 plus 1 equals 15. Well, this was formed too. 1 plus what equals 15? 14. 0, neutrons are 0, plus 7 is 7. 1 plus what is 7? 6. What element is 6? Carbon. Did you know that in the atmosphere, by itself, just because of particles from space, that nitrogen in the atmosphere can be changed into carbon-14? Now, there's huge amounts of carbon-12 on our planet. and there's only a certain amount of carbon-14. Now later you'll find out that if you have this much, if this much is, if I take any plant and I take it apart, and I say, well, most of your carbon atoms are carbon-12, but you do have some that are carbon-14. See that? And I take an animal apart. I do, so I had about the same ratio. You see that? Okay, got that. Well, what happens if they find something that's dead? Hey, I found a tree. I think it's been dead for 200 years. It's in the ground. It's an old canoe, and it has been a canoe. And how old do you think it is? Well, let's take a look. We expect this ratio, because that's what we see in modern day. We expect the same ratio, and that's a big assumption.
Good afternoon. This is not dismissal, so please don't get up to leave, students, but I do need to make one quick announcement to the bus riders for tomorrow. Please make sure you're on campus by 7:30, and please go through your normal screening with Ms. Shaw behind the Smith Building. Then you can head out between the weight room and the pavilion, and that is where you'll load the bus. Have a great day, Caldwell.
So let's say in a modern day plant, they don't say, carbon-12, you can come in. Carbon-14, you can't come in. They can't do it. If they're going to do it on photosynthesis, they've got to take any carbon they can get. So let's say in a living plant, it's a 1 to 100 ratio of carbon-14 to carbon-12. But it's been dead. What happens to things when they're dead? Do they take in any more carbon? No. Whatever carbon you have, you're left with. Now, let's wait. What's going to happen to the carbon-12 over time? Nothing. It's stable. What's going to happen to carbon-14? Decay. I'm going to decay into some other element. So now, instead of a 1 to 100 ratio, maybe it's going to be a 0.001 to 100 ratio, and they can estimate how old it is by the amount of carbon-14 that must have decayed. Now, it does assume that the C14-C12 ratio today was the same as it was 200 years ago, 2,000 years ago, 20,000 years ago, and they're going to tell you that they think it was. I don't know about that. But carbon-14 dating has to do with that. All right. Well, let's try this right here. One more. What happens to carbon-14 over time? Carbon-14. Now notice there's nothing over here, so I can't say bombarded. It wasn't bombarded. What do you call it when it changes into something? What's that D word? It decays into what? Nitrogen-14 and, whoa, what's that thing? What's that thing? Okay, so what kind of radiation does carbon-14 give off? Beta. What kind of radiation did uranium-238 give off? Alpha. All right. Okay, one more minute. How about one more? Now, one thing I want to show you, it's this is some high-level stuff. Matter of fact, when they, the Manhattan Project, you said you read about that? Okay. Very secretive. I don't know how nowadays they couldn't do it. But back then, we have drones and people who said, all right, give me some money. I want to be on TV. But back then, if somebody said, you're not going to say anything, you better not say anything. And they made a whole town. They made a whole town. And barbers and grocery stores and everything. And you're going to work on a Manhattan Project, and you're going to raise your family here, and you're going to live here. And you're not going to tell anybody what you're doing. You say, oh, they couldn't. They did. They did. Anyway, wait, where's that at? Oh, yeah. Well, they were doing some high-level stuff there, high-level. And here's one of the things that they did. Look right here. What if you bombard plutonium with a neutron? Well, it just becomes plutonium that's a little bit heavier. I got it. 239. I get it. It's still plutonium. What if you bombard it some more? Well, now it's plutonium 241. Well, then, once you get to this isotope, by itself, it wants to, what's that D word? It wants to decay into americium, and there we go. And now we have a new element, and guess which way we went? Which way did we go? From plutonium to what? Ooh, all the rest of these went uranium down to thorium. And this one goes from plutonium up to americium. You get that? So they figured out how to make elements higher than we've ever seen, and they can also let them decay also. I don't know if does this help you a little bit more understand? All right, I think one more day we're going to be in pretty good shape as far as basics, some of the basics. Hey, did everybody have the t-shirt? Okay. You know what? I understand, I actually do understand teenagers. I have three kids. I know, and I've been teaching a long, long time. I know what you could do tomorrow. You could say, I'm not doing that. I know what you, but can I tell you something? You can look back and say, why didn't I? When you get older, you say, what was it that didn't let me have fun tomorrow? Why didn't I just do my best tomorrow? Really? Because I want to be cool? And later you'll find out, what's the matter with me? I thought it'd be cool to sit back and not do anything. That was dumb. I'm hoping that I see all of you doing things tomorrow. Oh wait, I didn't have, Alan, you didn't have to hear that.